Usually when we think about like making a sculpture, there's this expectation of brute force. You hit a chisel with a hammer, chunks of marble fly off, and you're left with art.
Right, it's rough, but it works. You apply mechanical force, and the material just yields.
Exactly. And for thousands of years, I mean, that's roughly how we approached shaping metal too. You just scrape away what you don't need.
Yeah, it's a very intuitive, visible process. But then you step into the world of precision manufacturing.
Right, making parts that literally cannot fail, like aerospace gears or robotic joints. Suddenly, that hammer and chisel approach goes completely out the window. So, welcome to your custom deep dive. Today we're trading that hammer and chisel for a stack of engineering research to explore the extreme physics required to manufacture unbreakable, high-performance parts.
And the sheer amount of engineering required just to ensure a single piece of metal survives its operational life is, well, it's staggering. It requires manipulating physics on a level that almost sounds like magic.
Yeah, it really does, because before engineers can even think about fortifying a part, they have to actually cut the raw metal without ruining its structural integrity. And the ultimate enemy in the machine shop isn't like a dull blade, it's heat.
Oh, absolutely. Anytime you have metal grinding against metal to make a cut, you generate massive friction.
Right, makes sense.
And if you generate too much heat during that cut, you cause thermal distortion. The metal literally warps, and these invisible internal stresses build up.
Which is disastrous for delicate components, right? Like flex splines, those incredibly thin, flexible gears they use inside robotic arms. If a flex spline warps by even a fraction of a millimeter, the entire robot loses its precision.
Exactly, which is why they use high-speed machining, or HSM.
Okay, let's unpack this, because HSM is kind of like pulling a tablecloth out from under a set of dishes, right?
Yeah, that's actually a really great way to think about it.
Like by using ultra-high speeds, the cutting heat is carried away with the chips before it can even transfer into the metal. It prevents that thermal distortion on delicate parts.
What's fascinating here is that sometimes pure speed just isn't enough, especially when you're dealing with ultra-hard titanium or aerospace alloys.
Oh, right. So what happens then?
This is where ultrasonic-assisted machining comes in, or UAM. We're talking about using sound to cut metal.
Wait, using sound? Seriously?
Yeah, essentially. Engineers introduce high-frequency sound waves that vibrate the cutting tool at a microscopic level, literally thousands of times per second.
Okay, but how does vibrating the blade actually help it cut through something like solid titanium?
It creates a phenomenon called acoustic softening. The microscopic vibration drastically lowers the friction and the continuous cutting force required.
Oh, I get it. So instead of a plow dragging continuously through packed dirt, it's more like a tiny jackhammer chipping away at it.
Exactly. It ensures a much cleaner cut, prevents that heat buildup we were just talking about, and actually saves the tool from snapping.
Wow. Okay, so we've perfectly shaped the metal using speed and sound waves without melting it. But once that's done, the structural demands totally shift, right?
Right, the part is the correct shape, but the surface itself has to be fundamentally altered. You can't just leave it as is if it's going to survive constant friction in the real world.
So this is where we get into micro armor, right? How do they actually do that?
Well, there are a few methods. Sometimes they physically crush the outer layer using diamond burnishing. They take actual diamond-tipped tools and press them incredibly hard along the surface.
Just squeezing the metal with diamonds.
Yeah, particularly along the transition fillets of a shaft. It compresses the crystal structure of the metal to maximize hardness and smooth out any microscopic ridges left from the cutting phase.
Okay, here's where it gets really interesting. I was looking at the notes on the next method, laser shock peening. And honestly, it sounds incredibly excessive. Like, are standard manufacturing techniques really leaving gears so fragile that we have to shoot them with lasers just to eliminate invisible microcracks?
If we connect this to the bigger picture, maximizing fatigue life means you absolutely have to stop microscopic flaws before they can grow. Even the most perfect traditional manufacturing leaves invisible imperfections.
Like tiny scratches and stuff?
Yeah, tiny scratches or stress risers. Under a constant heavy load, a microscopic crack at the root of a gear will eventually propagate, and the whole gear just snaps.
Oh, wow. So what does the laser actually do to stop that?
Well, laser shock peening blasts the gear roots with laser-induced plasma shock waves. The sheer force of that shock wave creates deep compressive stress, literally driving the metal molecules closer together.
So it just locks those potential microcracks shut so they can't ever pull apart.
Precisely.
I mean, we're using lasers to force molecules together. That is wild. And then there's hard anodizing for aluminum parts, right? I assume they aren't just painting a protective coating on.
Oh, not at all. Hard anodizing uses electrochemistry. They put the part in a freezing acid bath and run an electrical current through it to force the aluminum surface to oxidize.
Wait, so they're growing the armor out of the metal itself?
Exactly. They grow a thick, hard oxide film that becomes part of the aluminum. It provides the ultimate wear resistance.
So what does this all mean for you listening? It means true precision engineering requires an absolute arsenal of heat, sound, diamonds, lasers, and chemistry.
It really does. It's the ultimate manipulation of material science.
For sure. So the next time you rely on a flawless piece of technology, think about the microscopic, highly controlled violence like laser shockwaves and diamond squeezing it took just to make sure those parts survive the real world.